Okay, hi everyone. Thank you, Hamant, for the introduction. Like you said, my name's Hazel. I am presenting on formalizing a new syntax construct in gradual verification, and specifically how that kind of interplays with ownership and the challenges that poses in the face of ownership. And this is work I did with Long, one of Dr. Aldrich's PhD students, and Dr. Aldrich in my REU this summer at CMU. And so to get started, kind of for the motivation for this and the place it takes up in the existing literature, we're discussing unfolding expressions, which are, as you might be able to guess, a type of expression that you can use to more concisely and expressively communicate information about ownership when you're writing your specifications. And these are commonly used in real-world programs implemented in several verifiers. And we need to check that these are implemented in a way that's sound, because otherwise the verifier, we don't know whether the verifier is actually checking the things we expect it to be checking. And so to address that, we are working on the formal semantics and a proof of soundness for how unfolding expressions are evaluated in gradual verification. And this is because gradual verification is a conservative extension of static verification, like Dr. Aldrich mentioned. This proof of soundness and the semantics will apply to both static verification and gradual verification. And so to get started with looking at precisely what an unfolding expression is and what it does and why we should care about them, we have some background we need to cover first. So to start, Viper, we're building on the Viper verification infrastructure, which is used for building static verifiers. It provides an intermediate representation, kind of like when you compile programs, except in this case, we use it for verifying programs rather than compiling. It also provides a symbolic execution backend you can use to statically verify programs in that intermediate representation language. And in Viper, we use recursive predicates to specify our data structures and encapsulate ownership over these data structures. So for example, these can just hold arbitrary facts. Like this is even predicate, we can just check whether an integer is even, and we'll get some more complicated examples that interact with ownership in the next couple slides. And one of the important things to note about these predicates and how we work with them is that they are interpreted using isorecursive semantics, which means that if we have a predicate, the instance of the predicate is different from the information that we have inside its body, which makes it difficult to reason about ownership when your accessibility predicates are contained inside other user-defined predicates. And we're building upon implicit dynamic frames, which is a variation of separation logic where you specify your heap ownership and content separately rather than together. And so to start discussing with the isorecursive semantics, like I just mentioned, we can have predicates like this that contain accessibility predicates to specify ownerships to data structures like this test struct. And we can see here, we have kind of distinct notions of what it means to have P of A and the accessibility predicate for the field F of A, even though we define these to be the same thing. And so to exchange between these separate notions, we use unfolds and folds, which will just take, unfold will take a predicate instance to the information in its body. And then if we want to get the predicate instance back from the information there, we can fold an instance of that predicate. And so this is relevant to ownership specifically in this context because, like we said, these can contain accessibility predicates, which specify accessing heap locations. And then we can use these permissions inside the predicate once we've unfolded it, but not while the predicate is folded. And this is useful because when we write specifications, we need to make sure that they contain all the necessary permissions to be well defined so that we can execute them like Dr. Aldrich said. And so in this example, we have an accessibility predicate here. But to access it from outside of the predicate, we need to first unfold the predicate. And so to look at a little bit more complicated of an example for this, we're going to start with a linked list, just contains an integer and is a pointer to the next node in the list. And we are going to specify this with a recursive predicate. Like we said, this just checks whether the list is empty. And then if the list isn't empty, we make sure we have access to the two fields and that the rest of the nodes after this one also constitute a linked list using this predicate recursively. So this is really helpful for encapsulating ownership of our data structures. Like linked lists in this case, we can also do this with things like trees and other recursive data structures. This is using the notion of predicates that we talked about before, where these are self-framing assertions where we give all the accessibility predicates we need, and then we can specify some facts about our data structures. And so, this is just an overview of what we said. And if we have an instance of this list n predicate specifying some list, we know that this predicate instance contains an accessibility predicate for n next. But if we're trying to use that accessibility predicate from outside of the instance of list n, we need to explicitly unfold that list predicate. So how do we do that from inside the same specification? So I'll show you a little bit of what I mean. And assuming your list isn't empty, because that's not really a useful case to reason about here. So we have this accessibility predicate inside our list predicate, assuming it's non-null. And then here we are going to look at an example where this is a function that takes in a linked list and just truncates it by cutting off the rest of the nodes after the first one. And we have this in the post condition, the ensures clause there. We state that, if we take in a non-empty linked list, then the result will be a non-empty linked list, which only has one node. We specify that by saying the rest of the list after the first node is null. We also have the code for the function here, but we're mostly just going to be working with this specification and this post condition. And so, since the result is going to be non-empty, we need to specify that the rest of the nodes after the first one are going to be cut off of the list. And so to do that, we need to make sure we have access to the pointer to the next node after the first one. And currently, the accessibility predicate for n next lives inside list n, like we said. So as we have it right now, this specification doesn't verify. Although it makes sense in terms of defining the actual functional behavior of the program, we don't have ownership of the n next field because that accessibility predicate lives inside the list n predicate instance. So to address that, we can use unfolding expressions, which allow us to temporarily open this list n predicate, look inside, and take out the permissions we need to frame the evaluation of the expression, and then refold the predicate nicely when it's done. And I'd also like to note that these are a thing that are used in real programs, like real-world verified programs. So for example, if we're using the Gobra verifier, Go has a verified standard library, and it also has verified Scion, which is a project to verify the Scion routing protocol. The syntax here looks different from what we're looking at, just because this is Go and the Gobra verifier. So don't worry if it looks weird, that's normal. I don't know Go, so I'm not really looking into it that hard. But in this example, we have an unfolding expression here like we've been looking at. This comes from the implementation of multi-precision signed integers in verified Scion. And the predicate we're unfolding here is this x.mem predicate, which just specifies access to all the underlying memory locations in the representation of the multi-precision signed integer. And so to kind of address why we need to formalize this in order to, build upon, to show the soundness of the verifier and how we evaluate unfolding expressions. These haven't been included in a proof of soundness or a formalization of the semantics in any static verifier yet. We do have a formalization for certain parts of the Viper verification infrastructure, via a formalization of gradual verification previously, but having a formalization that includes this will help us ensure that any implementation is done correctly, because we need to make sure that the implementations of the verifiers we're working with are sound, so that we're sure when a verifier passes a program that the program meets its specifications. And so we're going to look at this in more broadly than static verification, the context of gradual verification. Dr. Aldrich already talked about this. This will mostly be a recap, which means I'm going to hand wave some things he talked about a little bit. We're going to discuss the formalization and the theoretical aspects more than the implementation of it as well. So we're going to look at the same example with truncating a linked list, and we're thinking about fully specifying this program and writing this full specification up front. If we do this, we've got a high upfront cost for developers. Like he said, it's not super incremental because you have to have this full specification before you can debug. So to address that, gradual verification is introduced to allow you to write explicitly partial specifications that are backed by adding runtime checks wherever necessary, and we can just leave these blank. We can also add static information as we go on to decrease the performance impacts of runtime checking and to continually work towards a full specification. And so we've chosen gradual verification as the context for doing this work because ownership is kind of more interesting to reason about in this setting. Since we have to think about both static and dynamic checking, you have to keep track of the owned heap locations at runtime and while statically verifying, which is actually different in those both cases. And we also have to think about the fact that predicates are interpreted differently at runtime than they are during static verification, which we'll also discuss more in a minute. And since gradual verification is a conservative extension of static verification, if we formalize and do a proof of soundness for gradual verification, it'll also apply to static verification, which is super helpful. And like I said, this makes ownership a little more interesting to think about. And so specifically on that, we can have the partial specifications backed by runtime checks that can include accessibility predicates. And we also need to keep in mind framing. Framing is kind of our why we need to worry about ownership when we're thinking about gradual verification. Before we check any of our specifications, we need to make sure that they have ownership of all the fields they need to properly be checked. Like Dr. Aldrich said, we need to ensure all our specifications are executable before we go and check them. So framing is how we do that. So some examples of predicates that aren't properly framed, or specifications, sorry, that aren't properly framed. If we just have, access to the field F of the object X or the field G here, neither of these are self-framed because we need to make sure we have access to the field F of the object X ahead of time. So to do that, there are several ways we can make this self-framing. We can either add an accessibility predicate specifying access to F, or we can use the imprecision, the question mark, and this can be strengthened into the accessibility predicate. And so to look at an example that kind of motivates how we develop the evaluation semantics for unfolding expressions, we're gonna kind of go over the formal semantics, or an example that demonstrates the formal semantics for how we've defined these. This was already implemented in a past extension to gradual verification, but having the formal semantics, like we said, helps us check the implementation. And it actually did do that because we found a soundness bug in the verifier having these formal semantics. And so we're building on a past formal system for gradual verification because there's a past formalization using symbolic execution. And with this symbolic execution system, there are 4 kind of fundamental operations we can do with our expression statements and specifications. So the first and last one, evaluation and execution, kind of relate to symbolically running our code, where we are executing our programs with symbolic values rather than concrete ones. And the middle two, produce and consume, relate to what we know and how we interact with the specifications we have. And we're specifically going to be extending this symbolic evaluation one, since unfolding expressions are a kind of expression. So we're going to look at how we evaluate this unfolding expression in the context of the truncate example we've already been looking at. So we know before we even start evaluating this, we know that list n holds because we've added it before the rest of this post condition. So we have an instance of list n ahead of this, and now we can start evaluating. So first thing, we're going to open up our predicate to use the facts inside when we evaluate this expression. So when we unfold this list n predicate, we lose access to our instance of that, but we gain access to n next and the other facts that are specified inside the predicate, like the integer value of that node and the rest of the linked list. And then now that we have these permissions, we can evaluate this expression without an error this time. So we can check whether the next node is null as specified. And then going from there, after we've evaluated the expression, we can refold it. And this loses the information about ownership we had with the accessibility predicates, but we get our instance of list n folded back, so we're still satisfying our post condition. And so that's kind of how we go about evaluating these broadly, but there are some specific challenges we've encountered in building this formalization up to fit that intuition. And so the first one we can run into is we can have issues with unbounded recursion when we are evaluating unfolding expressions in this way. So in this example, we can see we have a predicate on a list, and we're not going to focus that much on what this does specifically, but the one thing to note is that we have another unfolding expression in here. And so when we try to use an unfolding expression with an instance of this predicate, what will happen is we'll unfold an instance, which will want to unfold another instance applying to the next node, and so forth and so on. And this won't terminate in static verification because we have symbolic values rather than concrete values. So at each step, it'll branch depending on whether the predicate could have terminated or not. So at a certain point to address this, we just cut off the recursion. I like to think of this as we just kind of block it off and you can't go any further. So we keep track of the predicates you've already seen when you're evaluating one. And after a certain depth of mutual or simple recursion, it just gets replaced with a symbolic value that doesn't carry the same information. This approach is theoretically incomplete, but this isn't really something you observe in practice because you would need to manually unfold to the same depth that the recursion gets cut off at, which isn't a super common use case you're working with. Another one of the challenges is with isorecursive and equirecursive framing. So like we mentioned, isorecursive framing is used with the static semantics for unfolding expressions, but we need to think about predicates differently at runtime. So we use equirecursive semantics where predicates are equal to their full unrolling at runtime rather than having them be distinct from the information in their bodies. And this means we don't really need to worry about things like folding or unfolding predicates at runtime. So checking whether our expressions are properly framed with ownership of the appropriate fields can be more difficult, especially when working with unfolding expressions in this case, because we need to reason about it super differently statically in the isorecursive case than we do at runtime in the dynamic case. And then one more of the challenges we've encountered along the way is that unfolding expressions kind of combine predicates and expressions in a way that we haven't seen in the rest of the formal system for gradual verification yet. And this can make it more difficult to work on our proof of soundness because we need to avoid circular reasoning with our proofs. And since predicates already rely on expressions, since our predicates can contain heap-dependent expressions to specify, we need to make sure we aren't circularly reasoning between our lemmas about predicates and our lemmas about expressions. And so for future work, continuing to expand upon this, like Dr. Aldrich showed, gradual verification has been kind of actively developed for a long time. And so there's always more to build on with interesting implications and repercussions we can discuss. So the first thing we're continuing to work on is our proof of soundness. We're using a progress preservation formulation for soundness, similar to the one we see with type systems commonly. We change the definitions of progress and preservations so that it applies to the verifier, but we still have similar principles here. And we also have to update the rest of this proof of soundness, since there is one, but it hasn't included unfolding expressions yet. And we've done a lot of the lemmas for expression evaluation, but there are also some ways adding unfolding expression has changed the rest of the formal system that we have to account for. And so for the broader impact of this work, unfolding expressions are super useful for increasing the expressiveness of verifier, and we see them in real world programs with verifiers like Gobra based on Viper as well. So having this formalization can help us check implementations to make sure everything is sound. In terms of our long-term vision and our higher level vision for working on formal verification, this isn't something we see super likely to be used manually in the future, since we're working towards providing more intuitive abstractions for verification so that developers don't have to manually work with things like this. And one of the things we are considering working towards to uphold this is bringing gradual verification into a language with a type system that contains ownership info. So like, for example, Rust, I couldn't get away with not mentioning Rust in this workshop, I fear, but the type system info from Rust with the borrow checker can automate a lot of the specifications that developers have to manually write, like folding and unfolding predicates, and it already has a strong formal verification community. So bringing gradual verification into Rust could help build a new level of abstraction to make verification simpler and more intuitive for developers. And that's all. Do you have any questions?
I guess I can start. One thing that this sort of made me think of, and this might be like totally off base, is like what happens with unfolding expressions and ownership is you like take temporary ownership of like the thing inside a predicate and then give it back. And that has like this kind of borrowing flavor almost. I was wondering if you'd given any thought to the relationship between those things.
Yeah, that's something we've talked about at like a high level. But not like super in the weeds with that yet. It's something we've like pondered a little bit, but not in depth yet. But yeah, there is like an interesting connection there. I'm thinking of a paper, but I can't remember what it is. But yeah, like with ownership type systems, the notion of like unfolding and folding predicates is similar to like how you manually, or how you would when verifying like pack and unpacked data structures, something to that effect. But yeah.
Sure, yeah.
Great talk.
Thank you.
One sort of technical question I was curious about is that we've just seen over the last two presentations a equirecursive and an isorecursive take in the same system. How does that interact?
So that's a really good question. Thank you. So with the equirecursive and isorecursive semantics, so you have to make sure that there's that these kind of move together in step between the static and dynamic semantics when you're proving soundness. So what we do to make sure those interact correctly is we have to define a notion of correspondence between the dynamic semantics and the static semantics, so that we can check whether, like, if we have a valid state in static verification, it corresponds to one in dynamic verification, which is where we handle most of the interplay between like connecting the isorecursive and equirecursive interpretations. Does that answer your question?
Yeah.
Okay. Awesome.
Hey, thanks for the great talk. At the end there, you were talking a bit about how it's like inconvenient to actually write all of this stuff manually, right? And I was thinking, rather than working at an entirely different level of abstraction or something, is it possible to just do some sort of like, I guess, inference or like automation there? Because at least in the examples that you showed, it seems like since like the reason you need the unfolding is just to get the access predicate you need to satisfy like another thing that you want to mention, and is that straightforward enough that you could just like have the system automatically like figure out what it needs to unfold to get that, or is it just like way more complicated in practice?
There is some like more broadly like in the space of formal verification. I know there's work on like specification repair and like specification synthesis. I know like specifically in the context of gradual verification, I think Jenna DiVincenzo, who Dr. Aldrich mentioned in his talk, has also been working on some things to that effect recently, but I'm not super sure about that. I'm certain there's like things you could do in that space. I'm just not super sure how it would look different for gradual verification yet, if that makes sense.
Okay, thanks.
Yeah.
All right, let's give the speaker another hand.